Hello everyone, welcome to the class. Today we will proceed ahead with the lasers. In the last class we started with the basics of the lasers, and therein we discussed Einstein's A and B coefficients. We understood what a population inversion is and why it is not possible to have two level system or two level lasers. And today we will formally start with the laser. Now, this slide is dedicated to the component of a laser. A laser consists of three main components. The first one is active medium. Active medium consists of ions, atoms and molecules. Now, these atoms, ions and molecules provide the discrete energy levels wherein we, after achieving population inversion, we get lasers, we get light out of these systems. The second important component of a laser is the pumping source. Now, we know that in a two level system, to achieve lasing we require population inversion. That means we want most of the electrons or most of the atom to be in excited state or to be in its upper energy state, and for this we need to provide energy, and the electrons sitting in the ground state, they absorb this energy and then they move up to the upper level. Now, the process of providing this energy or the process of pumping is furnished by some source, either optical or electrical, okay, and this is done by pumping source. The third component of a laser is optical resonator. Now, suppose we have achieved population inversion. Now, the electrons or the atoms will go down to the ground state and then it will emit photons. Now, these photons, if they are put between two mirrors, they will then bounce back and forth. Now, these two mirrors, they constitute or they work as an oscillator, because the photon oscillate between these two mirrors, and once it interacts with the inverted atomic system, it initiates the downward transition, which in turns provide us the gain. Yeah, therefore, optical resonator is a very important part of a laser. Okay, and the simplest example of optical resonator is two plane parallel mirrors, as is shown here in this figure. Now, here you see that this region is the active medium, where our atoms, molecules or ions are sitting, and then we pumped it externally, and due to this pumping population inversion is achieved, and these mirrors, they constitute or they behave as an oscillator, and these mirror thus create optical resonator, which compel the photon to bounce back and forth, and ultimately it gives a very high energy, directional, almost monochromatic, coherent beam of light, which we name as laser. Now, out of the two mirror, one mirror is highly reflecting and it has a reflectivity of around 100%, and the other mirror is semi transparent, which has a slightly small reflectivity, and due to this small value of reflectivity we get some transmittance, and laser output is received from this end of the cavity. Now, as I said before, active medium consists of a collection of atoms, molecules or ions, which is capable of amplifying light waves. Under normal circumstances, there are always a large number of atoms in the lower energy state than in the excited energy state. But what we do is that in order to have optical amplification, the medium has to be kept in a state of population inversion. And we know that population inversion is a state when the number of atoms in the upper energy state is larger than that in the lower energy state, and that is achieved through pumping. Now, pumping mechanism provides for obtaining a state of population inversion between a pair of energy levels of the atomic system. And when we have a state of population inversion, the input light beam can get amplified by stimulated emission. Yeah, if you remember, in the last class we studied about three phenomena: stimulated emission, spontaneous emission and absorption. Absorption is sometimes called stimulated absorption because it always happen in presence of some external field, some external photon. Okay. In laser we require stimulated emission because out of stimulated emission we get coherent output. Now, coming back to optical resonator, as you know, it's provide feedback to the system, and a medium with a population inversion is capable of amplification, but in order that it acts as an oscillator, a part of output energy must be fed back into the system. Such a feedback system is brought about by placing the active medium between a pair of mirror facing each other, or the active medium must be kept inside a cavity. The only role of a cavity is to provide feedback. A system formed by a pair of mirror facing each other is known as resonator. This is the simplest example of a resonator. And there are different kinds of resonator. The simplest one is shown here. You see there are two curved mirror facing each other, and this region is called resonator, which is surrounded by, this is bounded by these two mirrors, two spherical mirrors. Now, out of different kinds of resonators, the three important ones are mentioned here. The first one is plane parallel resonator. In this plane parallel resonator, we place two plane mirror facing each other, and then it provides feedback by reflecting photons back and forth. And here the radius of curvature of left mirror is R1 while right mirror is R2. Since we know they are plane parallel mirror, R1 and R2, they both will be equal to infinity. The second type of resonator is concentric spherical one. In this case, we have a spherical mirrors, okay, and they share the same center. Therefore, reflection would be such that the light would be there in this shaded region only, okay, and this point will work as a center. Here R1 would be equal to d by 2, and R2, the radius of curvature of the second mirror, is again d by 2, where d is the spacing between the mirror, the length of the cavity. Okay, here too d is this, the separation between the two mirrors, or the length, or you can say width of the cavity. Another important kind of resonator is confocal kind, and in this kind of resonator we have two mirrors which are spherical. Here the radius of curvature of first mirror is d, and radius of curvature is second mirror is also d. Now, in confocal mirror, the energy or the photons would be in this shaded region. Okay, these are the different kinds of resonators which are predominantly used. Okay, but apart from this, there are also resonators in which one mirror is curved while other is flat. Okay, here the photons will exist in this region, in this shaded region. There are other kind of resonators also exist, but these are the important ones. Now, to achieve lasing, we require population inversion. Yeah, lower state atoms becomes excited and make a transition to the higher level when an external pumping is used. This we know. Yeah, if the electron is here, then if you pump it, then it goes into the upper energy state, and it only happens when we have some external source, and this is called absorption. Okay. Now, when the number of atoms in the upper energy state is larger than the number of atoms in the lower energy state, this situation is called population inversion, and this is represented by this. Yeah, that electrons, most of the electrons are in the upper energy state. Okay, and this is called population inversion. Now, lasing action is started when the system achieves the condition of population inversion. Whenever the number of atoms in the upper energy state is larger as compared to the ground state, as compared to the ground level, then only the number of downward transition would be larger than number of upward transition. and in this case only we get some output, and this is called lasing. Yeah. Therefore, lasing action is started only when the system achieve the condition of population inversion. Now, lasing action is not possible in the two level system, and we have already understood it, because we know that the rate of transition from lower energy state to upper energy state is proportional to N1, which is the carrier density in the ground state, and the rate of transition from upper state to lower state is proportional to N2. When and in two level system, we can at most have 50-50 distribution of carriers or electrons. We cannot go beyond 50% distribution in two level system. This we can prove using Einstein's A and B coefficients, and using this Einstein formulation we therefore can predict that lasing action or population inversion is not possible in two level atomic system. Okay, because say initially in the lower energy state the population is less, then what will happen is that the rate of downward transition would be larger, and after a while a situation will come wherein the population of lower and upper energy state is equal. In this situation, the upward rate of transition would be equal to the downward rate of transition. Okay, and this is the state of equilibrium. Okay, and in this and we cannot go beyond it as long as only two levels are involved. Okay, and therefore we cannot make a laser out of a two level atomic system, but in three level atomic system we can make a laser. Why? Because now the atoms or electrons from E1 level is pumped to higher energy state, which is E3 here. Okay. The pump has a frequency which is equal to E3 minus E1. Okay. Here H cross V nu is equal to E3 minus E1, and in this situation the electron will directly go to the third energy state. Okay. Now, the lifetime of this third energy level is very small, it is almost equal to roughly 10 to the power minus 8 seconds, and therefore, they quickly go downward. And in three level system, apart from this E1 and E2, E3 state, there is a E2 state which lie midway between E3 and E1, not exactly midway, which lie in between E3 and E1, and this transition which electron make from uppermost level to E2 level, it is very fast, and therefore, it is called rapid decay. Okay. This is a transition, and as soon as the electron reaches in E3 level, since the lifetime of E3 level is very small, lifetime means the duration in which the electron stay in a particular level. In E3 level, the lifetime of E3 level is 10 to the power minus 8 second. Therefore, the electrons which are coming in E3 level from E1 level, they will stay there only for 10 to the power minus 8 second. Okay. I repeat, the lifetime of an atomic level is the time duration for which the electron stay in that particular level. Okay. And this time duration here is very small, therefore, the electron population will quickly go down to E2 level, and E2 level usually have a longer lifetime, and it is roughly 10 to the power minus 3 second, which is much longer than 10 to the power minus 8 second, the lifetime of E3 level. Now, since the lifetime of E2 level is very long, very large, therefore, the electron will start to accumulate here. Okay, and therefore, population density of E2 level will increase rapidly, and due to this increase between E1 and E2, a state of population inversion would be achieved, and as soon as we have population inversion, we will get lasing between E2 and E1. Okay. I repeat, once we have population inversion between E2 and E1, we will have lasing action between E2 and E1, and a laser would be emitted of frequency such that H cross nu 1 would be equal to E2 minus E1. Okay. Nu 1 is angular frequency in equivalent to omega. Okay. Now, therefore, we can easily make laser out of a 3-level atomic system. Similarly, we can also make a laser out of 4-level atomic system. In 4-level atomic system, we have 4 energy levels, and pumping is usually done between E1 and E4, and then there is a rapid decay of electron or rapid transition of electron from E4 level to E3 level, and these rapid transitions are most of the time non-radiative in nature. It means while transiting down, the electron or atom does not radiate any light, does not radiate any energy. Okay. The excess energy is lost in heating the atomic system. Now, due to this fast transition, the charge carrier population increases rapidly here in E3 level, and slowly we achieve population inversion state between E3 and E2. Therefore, between E3 and E2 we see lasing, and laser light come out of this system due to the downward transition, stimulated emission happening between E3 and E2. Okay. Once the electrons are in the E2 state, they again go down to the E1 state. Okay. And this transition, because of the established population inversion, gives us laser. Okay. Now, a few examples of laser systems are solid state lasers, liquid lasers, gas lasers, semiconductor lasers. Now, in solid state laser, ruby, Nd YAG and Nd glass are most famous ones. Dye lasers are the examples of liquid lasers. Helium neon, argon ion and CO2 lasers are examples of gas lasers. In modern communication system, it is now semiconductors laser which are dominating the field. Okay. We will study about these lasers. Now, ruby laser was the first laser demonstrated in 1960 by Maiman. Now, ruby crystal, as the name suggests, the ruby crystal is there in this laser. Therefore, a ruby crystal is used as a lasing medium in ruby laser. Now, in this laser, it is not the pure ruby crystal, because ruby crystal is made up of aluminum oxide, Al2O3. Now, in this aluminum oxide, some of the aluminum atoms are replaced with chromium. Now, to pump the system, we use xenon or krypton flash lamp. Now, this flash lamp, they pump periodically the ruby crystal, chromium doped ruby crystal, and all the lasings happen in chromium ion. Chromium ion, upon receiving the light from the flash lamp, it absorbs the radiation, and this absorbed radiation are of wavelength 5500 angstrom and 4000 angstrom. Now, here you can see the energy levels of chromium ion. This is the ground state, and you see that it is absorbing 5500 angstrom and it is going up in energy level E1, while the absorption at wavelength 4000 angstrom lead the electron to the uppermost energy level, which is E2 level. Now, the lifetime of E1 and E2 energy levels are very less, and the electrons in these excited state, they rapidly decay down to this level, which we call M level. The M level is called metastable state, and it has a lifetime of around 3 milliseconds. Due to this longer lifetime, we achieve population inversion between metastable state and the ground state of the chromium, and this transition is the most important transition. Due to the population inversion, this radiative transition leads to laser, and we receive a laser output at wavelength 6943 angstrom. Now, similarly, Nd YAG and Nd glass lasers are also important. The energy levels of neodymium ion take part in laser emission. Now, both of these lasers, Nd YAG and Nd glass, they are solid state laser, and they both are 4-level laser. Now, make it a point, Nd in both the lasers stand for neodymium, while YAG stands for yttrium aluminum garnet. Okay. Now, Nd YAG laser, it has very relatively smaller line width, and therefore continuous or very high pulse repetition rate operation, the Nd YAG laser is preferred over Nd glass laser. Since the line width of Nd glass laser is large, for high energy pulsed operation, Nd glass lasers may be preferred. Okay. Now, coming to the wavelength of operation, Nd YAG laser gives us laser emission at wavelength 10,641 angstrom, while Nd glass laser gives us emission at wavelength 10,623 angstrom. Now, coming to gas laser, the most important and widely used and studied laser is helium neon laser. This is the first gas laser which operated successfully. In this laser, helium neon is the active medium. Mixture of helium and neon gas is used as a lasing medium in this laser. Since the gas atoms are characterized by sharp energy levels, therefore electric discharge is used as a pump here, and very popular output wavelength, which is 6328 angstrom, 6328 angstrom is emitted in helium neon laser, and it has a wide application. Apart from this wavelength, this laser emits two other wavelengths which is also very important, and these two outputs lie at 1.15 micrometer and 3.39 micrometer. Apart from helium neon laser, argon ion laser is another important gas laser. In argon ion laser, ionized argon atom is used as an active medium. Okay. Now, this laser, it emits various discrete lines in wavelength region lying between 3500 to 5200 angstrom. In this wavelength band, this laser emits several wavelengths, it emits several discrete lines. A particular wavelength out of many possible line is chosen by placing a dispersive prism inside cavity close to one of the mirrors. Now, if you put a prism close to one of the mirror, then what will the prism do is that it will disperse the light in different directions. Now, one wavelength will go in one direction, while other wavelength will go in different direction. Now, since the path of travel of different wavelengths are different, we can easily pick a particular wavelength of our interest. Okay. The typical output power in a continuous wave argon ion laser is between 3 to 5 watt, and some popular emission wavelengths are 5145 angstrom, 4965 angstrom, 4880 angstrom, and so on. There are several other. The next important laser is this semiconductor laser. They are widely used in our communication system nowadays. As the name suggests, these lasers use semiconductor as the lasing medium. Since it is a solid state laser, and therefore they are not bulky, of course, yeah, and therefore the specific advantages of semiconductor lasers are small size, low cost, capability of direct modulation into gigahertz region. Okay, we can directly modulate this laser at a very high speed in the gigahertz region, and direct pumping with conventional electronic circuitry. Here we do not require to pump optically, we do not require flash lamp. The electric pumping will do, and it will give us population inversion. Therefore, they are very easy to operate, they are low cost. The light emission from a semiconductor is a consequence of the recombination of electrons and holes at a p-n junction when current is passed through the diode. P-n junction is the main component of this semiconductor device. Now, when a light is passed, then electron and holes at p-n junction, they recombine due to the specific design, and out of this recombination we get photon, and these photons at the output they give us laser. Now, when a current is passed through a p-n junction under forward bias, the injected electrons and holes will increase the density of electron in the conduction band and holes in the valence band, and at some value of current the stimulated emission rate will exceed the absorption rate and amplification begins. Okay. Keep it in mind that we have a laser cavity, and this laser cavity is bounded in lateral direction, that is they are bounded here, but they are not bounded here, or they are not bounded here. From the top and bottom side they are open, and therefore, out of diffraction some light may leak through, okay, and it will contribute to the losses. Okay. The mirrors are also not perfect, the coupling to the mirrors are also not perfect, there are absorption losses in the active medium also. Out of these losses we always lose a part of the light which is generated into the active medium. Now, when the generated light is larger than the loss which the system is seeing within the optical cavity, then only we see some output, okay, and then only we see some amplification of the light. Now, at some threshold value of current, this amplification happens, yeah, because if you increase the current, it will result into larger rate of stimulated emission, more photon would be emitted, but these photon would be lost in compensating the loss of the system. But if you keep pumping the system, if you keep increasing the current, then at some threshold value the loss would be equal to gain, okay, and soon after if you increase a current a bit more, you will have huge amount of gain at the output, huge amount of light would be seen at the laser output. Okay. Therefore, at some threshold value of current, amplification will overcome the losses in the cavity, and the laser will begin to emit the coherent radiation, okay, which we see in all types of laser. Okay. These were the different kinds of laser, but okay, few more important properties of this semiconductor laser is that there exist two configurations of this semiconductor laser. One is called homojunction semiconductor laser and another is called heterojunction. In homojunction semiconductor laser, the large threshold current is required, while a significant reduction in threshold current is seen in heterojunction semiconductor laser. Okay, I repeat, a significant reduction in threshold current is achieved by forming heterojunction. In heterojunction semiconductor, what happens is that the energy bands, they do not match, okay. But in present day, lasers are based on double heterojunction, in which a thin active layer of semiconductor with a narrow band gap is sandwiched between the two larger band gap semiconductor. This can be understood through this diagram. This is the conduction band and this is the valence band. This is the conduction band edge and valence band edge instead. Yeah. Now, this is the thin active layer inside the semiconductor laser. Now, in case of double heterostructure laser, we will have conduction and valence band of other semiconductor which is sandwiching this thin layer. Okay, let me explain it. Now, this is again conduction band edge and this is valence band edge. Now, this region here is our thin active layer of semiconductor lie. Okay, the thin layer of semiconductor lie in this region, and its band gap you can see it is smaller. This difference between conduction and valence band edge here is smaller as compared to this difference. This is called sandwiching layer or barrier layer. Okay. Now, the conduction band of this material is the conduction band lower band edge of this material is different from this material, and similarly the valence band edge of this material is different from this material. Due to this difference, we see that the conduction band of thin active layer of semiconductor is closer to that of valence band, and therefore, this energy gap is smaller. Similarly, the material lying here, it has different conduction and valence bands. Okay. Now, you see that the energy gap difference appears and here and here at two places. This is first place, this is second place. At these 2 points, the energy level difference appear. There is a step. Okay. And this step is called heterostructure or heterojunction, and there are two such steps, therefore, this structure is called double heterojunction. Now, if you pump the system, suppose we are pumping it electrically, we are doing some pumping here, an ammeter is here which is measuring current. There what will it do is that it will put charge carriers here, and ultimately all charge carriers will come down to the lowest part of conduction band, and therefore, the most probable transition would be in this region, thin region, this thin region. Okay, and this increases the efficiency of double heterojunctions. The barrier level not only confine the charge carriers, okay, this is called barrier levels. They not only confine the charge carriers, but they also play a role in guiding the light. Therefore, they make a waveguide out of the laser, and we see a very beautiful output, directional monochromatic, almost monochromatic light from these semiconductor double heterojunction semiconductor lasers. And this is all about the laser, and I end my lecture here, and thank you for joining me, and see you in the next class.